Welcome to the last slot of the conference. Thank you much for, well, congratulations to making it to the last slot of the conference first. My name is Alexander Chatzizacharias. Are there any other Greek people sitting here by any chance? Great, so there are two people that can pronounce my last name here, so it's pretty cool. At least I assume you can pronounce my last name. Perfect. I have a couple of hobbies. I boulder from time to time. If you sit behind a computer all day, sometimes you need to get some exercise. I do have a way too expensive Magic the Gathering collection, fortunately/unfortunately, and I play a lot of games. I played really a lot of video games. I also studied games, and you'll see that coming back a little bit during the session. Are there any other gamers sitting here? Good, a couple, nice. So hopefully some of my jokes will land with you guys. I work at a consultancy here in the Netherlands called J-Driven. We're with like 30 people, Java enthusiasts, that we're just working on cool stuff on the GVM. And that's all I had to say about myself. So about this talk, roughly 1.5 years ago now, if I remember, like December/January, last year, ChatGPT was released to the crowd, right? So we got to play with LLMs through a chat interface. It was amazing. I was also amazed by it. I was like, whoa, this is so cool. And being a programmer that I am, I decided, well, I'll just make my own ChatGPT. How difficult can it be? Well, in retrospect, it's quite difficult. And in retrospect, it also costs a lot of money, which I didn't necessarily have. But on my journey to find how ChatGPT worked or how these large language models work, there was one term that kept coming back, and that term was vector databases. So a lot of these AI applications, LLMs or GPTs, used a vector database somewhere in their stack. And that got me thinking, okay, what is a vector database? How does it work? Coming a little bit from gaming, I used to do a lot of things with vectors. So I want to show you what I did to discover vector database for myself, and hopefully inspire you to maybe do something cool with them as well. So that's why this talk. Before we talk about vector databases, there's a very important word there, vectors. Are there any mathematicians sitting here by any chance? Great. So if I say something very stupid, please feel free to correct me. I'm no mathematician myself. So mathematically speaking, when you talk about vectors, this is how most of the times are noted. So you see a letter with an arrow above them. And vectors are constructs, mathematical constructs that are very good at encoding a certain length and direction. That is what they're mostly used for. But it's not necessarily what we'll be using them for. A vector has a certain dimensionality. This is a vector with 2 dimensions. This is a vector with 3 dimensions. And this is a vector with 8 dimensions. Now, I'll just assume all of you are software engineers here. If you look at this, probably the first thing that you think is, this is an array of 8 numbers. And that is actually pretty much correct. So the dimensionality of a vector can be seen as the length of an array of numbers. And the numbers can be anything. They can be floating points, or they can be integers. Different models work with different inputs. So how do we use these vectors? We have a piece of text. This started happening roughly 11 years ago. We have this piece of text, and then we create a vector representation of that piece of text. And it started with text, so how can we create a vector representation or a numerical representation of, well, this text, and then continued with images. So we have an image, and then, okay, we create a numerical representation of that image. And then we went on to audio, video, and now we are in a state where we're trying to vectorize pretty much everything. So think about 3D models, point clouds, you name it. Okay, and that happens through machine learning. And these vectorization techniques are called embedding models. So who here has heard of the term embedding endpoint? Okay, a couple people. So when you read or hear about an embedding endpoint, that is an endpoint that you can call, often from OpenAI or Hugging Face, that you can send your data, and they'll send you back the numerical representation of that data, the vectors of your data. And that is done through machine learned models that were trained over huge data sets to vectorize that data. There are a lot of vectorization techniques out there. The first one was released by Google 11 years ago, was called Word2Vec, and a couple of years later, GloVe. And these first two iterations had a huge problem. They didn't understand context. So a word with the same meaning in different contexts, or different meanings in different contexts, had the same vector representation, which was an issue, right? And then the transformer revolution happened a couple of years later, where transformer models were released, and then these models could actually understand context. So a word with different meanings in different contexts actually had a different numerical representation. And that is really what allowed these large language models to pick up your input, understand the context, like the context that your input is in, and then give you the correct output. All right, so that was really short about vectors. Who here does know what a database is? Great. Some people are like, So a vector database is really a purpose-built database. It has one purpose and one purpose only, and that is to store and index high-dimensional vectors. That is really the purpose of a vector database. I tried using it as a time series. I tried using it as an event store. I was like, oh, how cool would it be if I used it as an event store during this talk? It really doesn't work. It has one purpose: store and retrieve vectors. And that retrieval and indexing within these databases happens using nearest neighbor search algorithms. And more of that later. And of course, you can store all kinds of associated metadata with your objects, and then you do queries, you get your data back, and you can build your front ends based on those vectors, on that data. All right. Let's say you have a very tech-illiterate project manager, and he's like, hey, I keep hearing this term, vector database. What is it? What can I do with it? This is what I told my tech-illiterate project manager when he came to me. It's a database that facilitates effortless and swift semantic search on your data. And there's a keyword here, which is semantic. So if you really need fast search on your data, you probably go with Elastic or some Lucene solution. But if you need semantic search on your data, so you're not really sure what your users might be inputting, it can be a very semantic text, then you can think about using a vector database. Now, what is really interesting, while nowadays there are being used almost exclusively for artificial intelligence applications or AI applications like large language models or ChatGPT, vector databases themselves have nothing really to do with AI. They're really specialized applications that are very good at storing these vectors, these numbers, and allow you to retrieve these numbers as quickly as possible. So, for example, if you want, you could just grab a Minecraft world and store your whole world in a vector database, and as you walk around, stream the world out of the vector database. Because in the end, the coordinate system are just numbers. It doesn't work very well. I tried, but it is possible. OK, so when you go and when you index in vector databases, they have a lot of algorithms that you can use. For example, linear search. That means that whenever there is a vector entered in the vector database, it's going to check its position versus all the other vectors in the vector database. As you might think, this doesn't scale very well. But then you have like k-nearest neighbors, which is a pretty known algorithm, or a shout out to Spotify for approximate nearest neighbors. Oh yeah, Enoi, and then the Voyager follow-up. And then a personal favorite of mine, hierarchical navigable small worlds. I never really thought I would have a favorite algorithm to that regard, but yeah, here we are, I guess. And all the algorithms work with so-called distance metrics. So for example, you can have Euclidean distance, which is basically how we measure distance between ourselves. Or cosine distance, Hamming distance, Manhattan distance, dot product. You might have heard of some of these metrics, might have not heard of some of these metrics. Doesn't really matter. In the end, you can think of, if you want, you can just grab one out of the box, use it, and then if you really want to fine-tune, you can start looking at different distance metrics. do you guys know what the distance and similarity is? The difference between the two. I assume the mathematicians here might have an idea. So when you're asking for distance, you're asking how close, how far away are two objects from each other. And when you're asking for similarity, you're asking how close are two objects from each other. Now, some of you are like, you're saying the same thing, but with different words. But what's important to know, I guess, is that when the distance is 0, two objects are very close to each other. And when the similarity is 1, two objects are very close to each other. And that's mostly done because similarity calculations are often cheaper for CPUs than distance calculations. And this distance and indexing calculations and everything happens within the so-called vector space. And this is very important. So when you start putting data in your vector database, you have to define a vector space for that data. You can think of it as your schema or your table. Every database has a different way of defining your vector space. And they mostly do it so that you are forced to use the same dimensionality. So that so you never check for vectors with different dimensionality against each other. Mathematically speaking, the calculations are possible, but you really don't want to do it because you get kind of finicky, weird results. Now, me being a gamer myself, the moment I heard the term vector space, I was like, well, I can probably make that. How hard can it be? So I tried to make a vector space of my data set. And this is one of the vectors in one of my data sets that I'll be showing today. And if you fly around, you will see more planets, which are all data points in the vector database, in my vector space. Now, I will be the first person to say this is not necessarily the most user-friendly way to look at your data, but it is the most fun way to look at your data. But what's really interesting, so these are actually all the data points, and what you really want to see is these clusters that are being formed. And clusters means that the objects, semantically speaking, are close to each other. So here I have, for example, a compound bow, and if I click here, I have a crossbow. So a compound bow and a crossbow are semantically speaking very similar to each other. And that means if a user searches for a bow, it will land somewhere in between and return these two objects. And that is exactly what makes vector databases so good at finding these, well, objects, semantic objects, or the semantic meaning, is that thanks to these the embedding models, you can have a vector space with semantically similar objects near to each other. All right. The vector database landscape is pretty volatile because, I mean, the whole AI landscape is pretty volatile, right? So there are new startups coming out every day. There are companies going bankrupt every day. But these are pretty much the biggest vendors right now that survived the first year after ChatGPT was released. Of course, Azure, AWS, Google Cloud, all the big vendors, Neo4j, Mongo, they also offer vectorization modules for their databases, if you want to go with that. I think what's really interesting for you guys is that on your right side, these databases are open source, and your left side are closed source. Redis has a vector database, which is part of Redis Stack, which is part of the closed source Redis stuff. Elastic is really funny because if you read their documentation or you read the website, they're like, yeah, we're open, we're so open, and then you keep reading, like, and it's like, but not really. So Elastic is closed source. You can't look at the source for the vector database. And for Postgres, you can install pgvector, which is an extension to use Postgres as a vector database. Now, what's really cool is some of these databases offer so-called built-in embeddings. That means when you send your textual data or image data to the database, it will grab that and it will vectorize it for you. And databases like pgvector or Pinecone don't have that. That means that you first have to do calls to an OpenAI API or a Hugging Face API to get your embeddings of your data, and then you can put the vector data in the vector database. Of course, they all want to earn money. So they offer managed services. They offer expensive managed services. I can tell you from experience, and I'm Dutch, and I really didn't like it. So the pay-as-you-go plans are quite, well, pricey. For PG Vector, you can use Supabase. You might have heard of it as a managed service. Or they all offer services on AWS or Azure or the big cloud providers. And of course, you want to query these databases. So most of them, well, all of them have the Python client, by the way, because Python is king when it comes to AI. But some of them have a REST API. Some of them have a Python client or a JavaScript client. Some you can call through good old SQL. And Vespa you can call through YQL. Does anybody know YQL? I think it stands for Yahoo Querying Language. I'm not joking, which is definitely a choice to make for your vector database. So yeah, so that is a little bit of a landscape. So let's see what we can do with a vector database. Let's implement our own search. So for my stack, I use VV8. I chose VV8 for the persistence. I have a Kotlin Spring Boot app as the backend service. Kotlin because it's the superior language of the JVM. Changed my mind. And then I use Unity 3D for the front end. Does anybody know Unity? Unity 3D, a couple of people. So if you don't know, Unity is a game engine. Unity was a very popular game engine a couple of months ago when they tried to shitify their product. So they really made headlines left and right, but I'm quite proficient with it, and I do not pay them, so I will keep using them for free. So I chose VV8 because it's open source. So I could really dig into the database code to see why it was not working. It is completely modular, so I could mix and match with embedding models that you run in Docker containers next to the database, and then could see, okay, this one works well, this doesn't work that well. The documentation, the Java client is actually pretty decent, so I do not use anything like LangChain4j or Spring AI or semantic kernel or anything like that. It's just pure the VV8 client in my backend service. And of course, I can run everything offline, which is pretty nice if you give a demo on stage like this. So the architecture of all the demos is pretty simple. Through REST calls, I'll be calling my backend, which does some preparation and then calls through the VV8 client library to the Docker image. Any architects sitting here? No one? Thank you. that is what I keep saying. It's a dying job. But so I had some architects at other sessions telling me, like, you can simplify this. You can remove your backend and just do calls through the front end directly to the Docker image, because I mean, in the end, it's just REST HTTP, which is true. But I'm a backend developer, and adding abstraction layers is literally my job. So that is what I did here as well, and that is what I'll be doing until the end of days. So for today, we'll be using cosine distance as our distance metrics for everything, hierarchical navigable small worlds as our indexing algorithm, and BERT ResNet 50 model and CLIP model for when we are vectorizing stuff and how that looks like and why you'll see in a bit. So cosine distance, this is the formula for it. What is interesting, I guess, for you is that if the distance comes out 0, that means that two vectors are identical. And if it comes out 2, that means that two vectors are completely opposite from each other. So let's say we have a Java class and a C# class, and we vectorize those. Then the distance between those vectors would be 0.2, pretty, because C# stole everything from Java, or so they say. And if we have a JavaScript script and a Java class and vectorize those, then, unless you do some really funny things in your Java classes, right? But yes, then it should be pretty opposite. Hierarchical navigable small worlds, it is really a tongue twister, are a little bit trickier to explain, so I tried to do it like this. So let's say we have all kinds of data that we want to put in a vector database. Every time that we insert something in a database, it's going to do a so-called proximity scan around it. and then it will connect itself to an X amount of closest other objects in the database. And it will keep doing that. So like that, we build a so-called adjacency graph, or a neighbor graph, or a friendship graph. It has a lot of names. In our case, of the 3 closest nodes to where you of the new object that entered the database. Then there is a random chance. In our case, it's like 60% that a data point is going to be duplicated in a higher layer. And then exactly the same thing is going to happen. In the higher layer, it's going to do another proximity scan and create another adjacency graph there. And then there is an even smaller chance, in our case, that's roughly 25%, that it's going to be duplicated in an even higher layer. So as you can see, we have a multi-graph structure where the yeah? So whenever, it's fine. Whenever you insert something, there is just a random chance of the algorithm has a chance that it will duplicate into the higher layer. And as you can see, the topmost graph is quite less dense than the bottom graph. And then let's say we do a search, or we're searching for a vector, and the vector ends up there. And that means that this is the closest data point in our vector database that we should return. Then we're going to do a search from the topmost layer, go to the closest node to where we want to go, and then use that as an entry point in the middle graph. Again, go to the closest node to where we want to go, and then again, use as an entry point in the most dense graph to go where we want to go. And like that, we'll find the node that we're searching for, the object that we're searching for. As you can see, like that, you can skip a lot of checks and a lot of steps that you otherwise would need to do. So you are sacrificing a little bit of data duplication. So your database will have more gigabytes of data for speed, pretty much, right? So again, let's say we want to find this vector over here or this object there. Again, from the same starting point, we'll go to the node closest to our destination. Do that again in the lower graph using the new entry point, and then again using that calculated object, we'll go where we want to go. And small algorithms like that, like this, is what really allows vector databases and to search through millions and millions of records within milliseconds and find you the vectors that you're searching for, which in my opinion is pretty cool. All right, so if you look at this, anybody recognizes where this is from? Yeah, just shout it. The Matrix. Yeah, I heard it. Somebody whispered it. I think it's the Matrix. Just said that. You should be proud. So yeah, the Matrix. Anybody that has not seen the original Matrix? Homework for tonight, maybe. So there is a scene in the Matrix where Neo asks for guns, lots and lots of guns, and they give him guns, lots of guns. But there is a very obvious plot hole here. How is he ever going to find the gun that he's searching for? So we're going to help him. We have a little CSV. And in that CSV, we have all kinds of weapons. And with 3 properties: the name of the weapon, the type of the weapon, and the range of the weapon. So for example, name, Excalibur, type, sword, and range short. And when we vectorize that, it's basically going to join them into one string, lowercase it, and we get weapon, Excalibur, sword, sword. If you want, you can even choose to vectorize the property names. Then it would become weapon, name, Excalibur, range short, type sword. In our case, we're not going to be doing that. So we only vectorize the actual data. And then the BERT model will translate that into a vector representation of 384 dimensions. And that is a little bit how the numbers look like of such a vector embedding. OK, if you look at the data set, it is really small. So this is like 50 weapons I put in database. Let's see what we're going to find. So I know you might be confused right now that I'm showing you a clip from the movie. It is not. So yeah, Trinity is saying, hey, are you sure? Neo's like, God dang right, I'm sure. And I'm very happy because the scene after, like with the elevator and then they break into the building, that was so cool. Anyway, maybe a little bit of a weird question. Does anybody have a favorite weapon? Or in Call of Duty, also allowed. A minigun. So let's, a minigun. It is not very mini, huh? Well, the vector database does think that it's mini. I don't have a minigun in my data set. And if we look at the distances here, you can see a minigun and an actual pistol has a distance of 0.4 from each other. Yeah? Oh, yeah? Sure, I can see. A minigun. No, it's another pistol. But for example, I can do a slingshot. The slingshot. You had a very quick eye when I looked at when I showed the data. But yeah, so this is. But you can of course do also a Japanese weapon, which will get you an Odachi, which is actually a Japanese weapon. So the embedding model, when I vectorized the Odachi, understood the context of, okay, this is a weapon originating in Japan, et cetera, et cetera, et cetera. And then when you actually search for Japanese weapon, you get the Odachi. Then you can also, for example, do something explosive. And you get an RPG, which is very explosive, by the way. So yeah, as you can see, but it's not foolproof, right? So if I don't know if anybody of you played Doom ever. You have a gun, the big gun. And if you see, I want the BFG, it's like, I don't know what this is. Here, have an M15 without a texture even. I mean, like, yeah. Yes. So exactly. So the input, because VV8 offers built-in embeddings, pretty much. I don't have to do calls to OpenAI. Is being vectorized into a vector representation, and then the distances of that vector representation with everything in the database is being checked, and I'm getting the closest result. And that is a very good question, because that does mean that given an input, you are never really sure what the output is going to be of your vector database. To me, that's beautiful, you know, a little bit of gambling, a little bit of, you know, you never know. But given the same input, the output is always the same. So for that you can be sure, but you cannot ever really be sure what that output is. Yes. Within the vector, within a certain vector space. Yeah, yeah. So, yeah. That's a very good assumption. All right. Anyone that plays Dungeons & Dragons here? Great. Oh, there's actually quite some people. Great. So if you don't resonate with Dungeons & Dragons, then whenever I say wizard, think of Harry Potter. So in Dungeons & Dragons, you have a lot of spells. We have a very forgetful wizard that walks through the, through the forest, and then at some point he's going to be ambushed by a thug, and we're going to help him find a spell to defeat the thug with, and again, using a BERT model. If you look at the data set, it is much bigger, right? I got the data from Kaggle, where you can find a lot of open source data sets, amazing. So these are all the spells in the Dungeons & Dragons player handbook. All right. Oh, don't rename. Anybody that played Baldur's Gate 3 by any chance? It's practically the same, right? Okay, so anybody has a favorite spell in Dungeons & Dragons? You want me to spell Mordecai? Jeez, Mordekainen's magnificent mansion, which is not from the player handbook, by the way. So let's see what we're going to find. Mordekainen's magnificent mansion. It's still there. How did I do in the spelling? Mordekainen's. Oh, two N's. I mean, I was pretty close. Yeah. And then we kill the thug. And then we bring him back for eternal torment. So it was funny. Once I gave this session, and Lisa, our keynote speaker, she shouted, "Can you search for explosive diarrhea?" I was like, how do you spell diarrhea? I'm not going to try. Then you can, for example, search for a fireball, which is very classic, right? And then you can indeed find the fireball. And then again, we can cast the fireball, kill the thug, death, bring him back. But I had to do a couple tricks to make this work as well, and still not perfect. If you look at how I import the data, I basically tell my vectorization module, I don't want you to vectorize most of the properties, like which classes can use this, which level can use this, what kind of cost does it have. I want you only to vectorize the name of the spell and the description of the spell, and then I create a very semantic description of the spell. So I put all the properties in a very semantic piece of text that I use as description for the spell. And like that, I make it a little bit easier to match what I'm searching for. Another way to do this is to split the text. So when you're in your AI, you'll hear about document splitter or text splitter. So you split the text in smaller segments, and then you still refer to the same object with a smaller segment. That's also a way to do this. Okay, let's do one last one. Anybody? Yeah? Sorry? No, no, I don't think so. Every embedding model does this differently, of course. But overall, no. What they do is words like the and they are being filtered out. So those are not really coming back in the vector representation. Yeah. One I really liked was JavaScript. And then you get web. But it gets better, and you'll see in a bit. All right. So this was, of course, text, but we can also do the same with images. Anybody that has played this game? So somebody's like, that was long ago. So Pokemon, to me, it's a very weird game. So you're on rails, and all you do is you ride around, you take pictures of Pokemon, and you throw apples at them. That's pretty much it. It's so weird, but it's so hugely popular. So many people play it. So we're going to try to recreate this. So we have Ash. He walks around in the forest. He sees a Pokemon. He flips his hat, because that is what Ash does. And then we're going to take basically we're going to take a capture of our camera frustum, send that to the database, and try to find the Pokemon that we're looking at. If you look at our data set, so here I have a CSV with an X amount of Pokemon, 721. When I watched Pokemon, there were like 160, so it goes fast, apparently. And I have icons of Pokemon. So this is, for example, this is. Okay, you guys know your stuff. And this is. Okay, and what is number 7? Yeah, you thought I would keep asking the easy questions. So who? Squirtle. Okay. Number 25? Okay. All right. How about number 288? Snorlax, ooh. Well, I mean, it's pretty, but as you can see, all the icons are they're similar, right? So white background and white and not transparent because the embedding model doesn't understand transparency. So it needs a color in a certain pixel. And they are all 300 by 300 and a very cartoony 2D image of the Pokemon. Again, got them off Kaggle. All right. So this is Ash, as you can obviously see. And this is, and if we take a picture, and then indeed we can find Pikachu. So we take a picture of what the image of what the camera is seeing, we base64 it, send it to the database, and we find what we're searching for, thankfully. And this Pokemon is? No, Pikachu again. And from this side, it is a Beautifly. And from somebody of you, he always returns Pikachu. Now it's a Xerneas. So as you can see, it's not perfect. You don't necessarily always find what you were actually searching for. Let's try another one. This is? No, it's a Joltik. If you look at what the camera sees, there on bottom, this is what the camera sees. So it sees the Pokemon as is, and yellow background. Can anybody guess what kind of yellow this is? It is Pikachu yellow, yes. So to make this work, at least with Pikachu, because the embedding model doesn't necessarily understand the context of Pokemon, that this is a Pokemon. My guess is because they're all afraid to be getting sued by Nintendo. It kind of defaults to colors and shapes. And I'm sending a very 3D image of a Pokemon to be cross-referenced with a very 2D image of a Pokemon. So it's a little bit tricky to match that. So what I did is I just made sure that the background was yellow, and then it would match Pikachu most of the times. But yeah, to solve this, either what you could do is you could either train your own model to understand what a Pokemon is, which might cost you a little bit of money, I guess. Or I could have taken different pictures of the Pokemon from different angles and store them in the database, have them all refer to the same Pokemon, and like that would be easier to find what I'm searching for. But I really want to show you that do not expect to just grab your data as is and put it in a vector database and it's semantically searchable. There is a chance that you need to do some preparation and create some data ingestion pipeline to make it really work as well as you want it to work. Yeah? So these are 512 by 512, the dimensionality. And of course, the higher your dimensionality, the vector dimension. The dimension of the vector is 512 for the images. And of course, the bigger your dimensionality, the more accurate your vector representation is, right? But the bigger the dimensionality, also the more expensive the distance calculation is between two vectors. Because suddenly you have to cross-check 1,000 numbers against each other, or 10,000, or 5,000, or 15,000. I run everything locally. So it's just a Docker image that I can pull off Hugging Face, and then I run it locally and just has abstracted all the Python crap, sorry for my, pardon my French, away from me. So I can just REST call to it. Yeah? Well, a GPU helps. Yes. But if you want, we can chat about this a bit. Yeah? All right. So our wizard is very forgetful. So he took a right turn. So he's back where he was. But right now, we're going to make things a little bit more gamey. So we're going to use a multimodal model. And that means that that is a model that can understand text and images in the same vector space. And that means that you can cross-reference images and text with each other. So you can search for text using an image, or you can search for an image using text, which is pretty great. So We're gonna try and find spell for him. Then using that spell, we're gonna the name of the spell. We're gonna cross-reference an icon data set, and hopefully find something cool to kill our thug with again. If you look at the data set, well, it's the same Dungeons & Dragons spells. Gee, I scrolled far. And if you look at the icons, this is basically what they look like. So all the icons, they're just, the name is icon, and then a number, and then .png. They're pretty good quality, 256 by 256. I bought this like 12 years ago or something from a Humble Bundle, if you've ever heard of it. Back then, my mother looked at me and was like, "You're wasting your money." Who's wasting their money now? I got to use them. So there is no labeling done with the icons or whatever. I just throw them through a clip model, and I throw the text that we'll be finding through a clip model again, and try to cross-reference and find a cool icon using that. All right. So anybody, anything specific? Not Mordekainen's magnificent mansion that wants to be searched? Explosive? Oh, sheep. I was like, are we going that way again? Storm of Vengeance, delayed blast, firewall, and a psychic scream. And then we can cast, for example, the psychic scream. And then now you see fireworks. And he flies higher. So bring back. So whenever I give a presentation, I have like this, this goal that I need to show an explosion somewhere. So I'll be doing that now. So if we go for a fireball, as you can see, fireball looks pretty much like a fireball, pretty good. Pyrotechnics also pretty good, and firebolt, yeah, could be classified as firebolt. And then we can cast the fireball. There it is. And that's my explosion quote I reached for the presentation. And then you can do, for example, sorry? Ice? Something icy. Let's see what we get. Investiture of ice, ice knife, which is a knife, not so which one of the three do you want to see? I assumed for you. And it's a different particle effect. So to me, if I make games like this, it's really cool that suddenly I don't need to label everything. I don't need to label particle effects. I can just throw everything in a vector database, cross-reference between each other. Then I'll get something back. I'll get it back in icon. Then I can just extract the average RGB color of the icon and just show a particle effect that matches that icon RGB. So yeah, like that, suddenly you can just do much more faster. So for example, I can do poison. Let's see what we get. And then we can kill him by protecting him from poison. And a really funny one, I want to confuse them with JavaScript. And then you get distort value, which is so on point. I love it. And I think it's, yeah, perfect. And then a very popular spell in Dungeons & Dragons is Wish. So then we can cast Wish, and then you can get Wish, which or Beacon of Hope or Ceremony. As you can see, the icons match pretty well the semantic meaning of Wish or Beacon of Hope. And we cast this. Oh, again, it's I wish him to explode. All right. I'm a huge metalhead. I don't know if there are other metalheads sitting here. I know one for sure. Any people that really hate metal music? Okay, good. Because the next one is all about metal. So anybody of the metalheads that knows what this is? So this is a band, a virtual band called Death Clock. They have a cartoon called The Metalocalypse, amazing cartoon. And they have a song, it's called the Duncan Hills Coffee Jingle. In my opinion, it is like the international anthem for coffee. especially being a developer and loving coffee. When it comes to metal music, there's like they really like to grunt, right? So if you ever heard metal, you know the grunt. A little bit difficult to understand if you have not looked up the lyrics sometimes, and especially if you want to, you know, Shazam for the lyrics or something like that, it can get a bit tricky. So we're going to make our own Shazam specifically for metal music. So in the database we have. I put all kinds of songs, for example, of Beyoncé, with all kinds of songs of Beyoncé with lyrics, Billie Eilish, the same, Ed Sheeran, Coldplay, and I have 3 metal songs vectorized in this vector space. I have Enter Sandman by Metallica. Many people should know this one. Through the Fire and the Flames by Dragon Force. If you ever played Guitar Hero back in the day, this was the bane of your existence. It was mine, for sure. And the Duncan Hills coffee jingle. And that is what we're searching for. So what we're going to do is we're going to use a transcribing model. It's called Whisper by OpenAI. And what Whisper does is it it listens to the audio and tries to transcribe the lyrics that are being played. And then every half a second, we're going to be querying the vector database with the last couple of words and trying to find the song that we're searching for. So who here thinks that we're going to find the song that we search for? A couple people, the optimists between us. Who thinks no way? One person, the pessimist between us. Who thinks it depends? It wouldn't be a software engineering conference either way, would it? All right. So let's hope, so it's now transcribing. Let's hope all the sound and everything works perfectly. It takes a little bit. There we are. So to your right side, you see the actual lyrics. On your left side, the transcribed lyrics. On the top, you see what we found from the vector database. Like Lady Gaga in this case. Beyoncé, very metal. Coldplay has a guitar at least. Stuck on Coldplay. Taylor Swift. Selena Gomez, arguably not very metal. Post Malone gets a bit harder at least. And what's really funny to me, every single time, without fail, during the solo, Ed Sheeran keeps coming back. So I don't know how high his voice is. Yes, yeah, yes. Sorry? It's not pitch, no. But somehow the transcription model is transcribing the guitar solo to something that apparently Ed Sheeran says a lot. Yeah, yeah. All right, so on that note, and seeing that I only have 1 minute left, thank you for watching. Skynet is going to rise. We all know that. It's happening. But I'm pretty sure that when Skynet rises, if we just start to grunt to each other, the AI will have no idea what we tell to each other because it couldn't transcribe and find anything. So yeah, thank you much for watching. If you have questions, feel free.